What's happening? Let's get this lab. 2211, lab 4, oscillations. I really did not like this lab. It made me crash out a lot. So here's my introduction. Purpose, we're going to observe and analyze the spring mass system. Compare that motion to an observed motion. Predict the motion to the observed motion. We're going to plot the change in position versus the observed motion. Plot the change in energy from the predicted values. We should get the results that delta E equals 0. And the predicted positions should be similar to the observed. We're going to be using Newton's second law, which is the F net equals ma, as well as F net equals the change in momentum, which is dp, or that's the derivative of momentum over time, dp dt. And then Vf equals Vi plus F net over m times delta t is the velocity update. And then we're going to use position update as well, which is Rf equals Ra plus the average velocity times delta t. Bang. Alright, and the big thing is the energy principle. Right, it's going to state that the change in total energy is equal to the work done from the surroundings plus the heat exchanged. Right, and some things to remember for this is that energy cannot be created or destroyed. The defined system is the spring, the earth, and the block. Surroundings are going to be everything else, but since the system includes the spring, the earth, and the block, so like the earth kind of encompasses everything, right? There's no surroundings, so no work is being done, so delta E will equal 0. That's just defined off rip. Some equations we're going to use, the delta E equals work plus the change in heat. Delta E equals delta K plus delta UG plus delta US, so the total change in energy is going to be the change in kinetic energy plus the change in gravitational energy plus the change in spring energy. K is 1/2 mv squared. UG is mgh, US is 1/2 ks squared. Bang. Alright, so here's my tracker, right? So I tracked the mass when the dude dropped it, and I got that graph. So that's giving it in like centimeters. So you had to convert all of that to meters pretty much, but you get the deal. Bang. So here's our initial conditions, right? So the initial velocity is going to be 0 because this shit's not moving. And then the position is that point, which I gathered from this, right? Negative 0.1 and negative 0.4 pretty much. And our spring constant, right, is from that predicted, or from the observed. And the length of the relaxed spring is also observed. And now we get into the code. So this is the code I use. First I'm going to go over these parts here. So this is calculating the kinetic energy. This is calculating the potential energy. This is calculating the spring energy. And this is going to give me my total energy. Right? So that's how we're going to kind of like, this is like the most important parts of here. And then over here, we're calculating the length of the spring at the given moment. Right? Here are our energy calculations, and this is just the update, the velocity update and the position update for the graphs. Okay, so here's our change in energy graph. As you can see, delta E sits at 0 because there's no change in energy. Bang. And the other ones, right, you see how they're all equal and opposite, right? So they're going to be canceling out. That's good, which means that delta E is going to be 0. So if you added up all of the values at a given point, it would be 0, which is a dub. Alright, here is the graphs of my predicted versus my observed. As you can see, like, they're pretty close. There's a little bit of error, but for the most part, like, the oscillation speeds are there. It's just the difference of the amplitudes that got a little bit goofy, but we're chilling with that. That's fine. What's it all mean? Was the energy principle satisfied? Yes, as I showed, it is, because we had like we had the graphs where the change in energy is 0 and everything adds up to be 0 from all the other energies, and the average oscillations for X was 2.08. The average oscillations for Y is 1.9. And this difference is due to unaccounted forces like drag or human error when I was doing the tracker. So I'm going to go back here. Right, so as you can see, if I'm going from the bottom of the oscillation to the bottom of the oscillation, right? It's close to 2.0 for the X. It's close to A for the Y. Bang.